In this mechanical system, we have two rotors that are externally meshed together with gears. We have an input torque on the first rotor, and ultimately we want to find how that input is going to affect the output of the angular velocity of the second rotor. Looking at the system here, we have rotor 1, the top rotor, that has a mass moment of inertia J1 about its longitudinal axis, and the second rotor, the lower rotor, has a mass moment of inertia J about its center axis. Each rotor is attached to a viscous damper, a rotational damper, with a damping coefficient of Ct. And we have degrees of freedom established, θ1 for the top rotor and θ for the bottom rotor for their respective angular positions. So given the sense of that degree of freedom, I will stick with that as we go through the derivation in this problem. So let's start with looking at ultimately what are we trying to find. We want to know the output velocity of the second rotor, which I will call capital omega, since it's a velocity, and the input is going to be the torque. And I will call that generic G to establish that it is a transfer function. So I want my output in this problem to be the angular velocity of the bottom rotor to the input torque put into the top rotor. Something else to notice in this problem is how the two rotors are attached. Again, they are meshed together with gears. To have a properly meshed gear, it's going to have to be true that the ratio of the radii of the gears is equal to the ratio of their number of teeth. So we are told that the top gear has N1 teeth and the bottom gear has N2 teeth. So they are properly meshed. So that ratio has to be true. And for this external gearing, that gear ratio is going to be negative omega over omega 1. So negative the angular velocity of the bottom rotor divided by the angular velocity of the top rotor. So that is coming from machine dynamics for fully or properly meshed gears. So let's start digging into this one. We need a transfer function, so it's a mechanical system. We start with free body diagram. So I'm going to look at the top rotor first. I'll give this a little bit of perspective when I draw it. So we have that main rotor there, and then we have another thinner shaft, and it's going to go to that larger gear. So it's only going around one axis here. So I'm going to say that that axis, because we've established the direction of θ1, I'm going to say that this is going to be, let's just say the x-axis. So then using right-hand rule, positive around that is going to be the θ1 direction. So let's look at the torques and forces that are acting on this rotor. So the θ1 is not force, it's just establishing the direction, which I copied to the right here. I do, though, have this input torque that is going to be positive around this x-axis, or it's going to be, when positive, with this θ1 direction. So I'll establish that here, and that is going to be T, my input torque. Now the input torque is the input into the system. It can vary in time. It's a function of time. Also acting on this, I have a rotational damper. A rotational damper is going to exert a moment on this shaft and ultimately on the rotor. So just like with the viscous dampers we saw for linear systems that are going to oppose basically the velocity, the direction of velocity that in a linear system, the same is going to be true here with rotational velocity. So again, I'm establishing that around this x-axis positive is the positive sense of the angular position, and thus the positive sense of the angular velocity. So always opposing that direction is going to be the torque or the moment from this rotational damper. So it's going to be the damping coefficient times the velocity. Here, the angular velocity. So θ1 is the position, θ1 dot is the angular velocity. Again, we want to pay attention to the direction here. This is not relative because one side of it is attached to the wall and the other to the rotor. It's always going to oppose the direction of our angular velocity. So when θ1 is positive, it's now going to be around the negative x-axis, and when theta 1 is negative, it's going to be around the positive x-axis. All right, we have our input torque, we have our viscous damping. Now we have to look at really where those gears are meshed together. What is happening there? Really, there's going to be at the interface where these gears are meshed together, they're going to rotate each other, or they're going to transfer energy to each other by the meshing of really the teeth at that location. So the bottom tooth of the top gear is going to push against the top tooth of the bottom gear. That's how energy is going to be transferred into our system. So there's different ways we could model this. I'm going to model this as really the force at the tooth on the bottom gear here. So if we are rotating around this positive x-axis, the direction ultimately is not too important, but we're going to have some force F. This is meant to be a straight line. It's a force. This is the bottom rotor's tooth exerting a force on the top rotor's tooth. And this F is a function of time. And that is going to be located a distance of R1, I will call it. That will be the radius of the first gear. Now do pay attention to what we are looking for here. We want to use only given parameters. So I am inventing this R1. If we look at the diagram, we are given the number of teeth. We are not given what the radii are, R1 or R2. But because they are fully meshed gears, we know that the ratio of the radii has to equal the ratio of the number of teeth. But I want to use this R1 when I get to my equations of motion in a moment. So I will come back to that. So that is the full free body diagram for the first picture, at least as far as the moments and the torques go. I'm going to move my coordinate system over because I also need here to draw the inertia. The left side is my moments and forces that cause moments. I'll have a very simplified drawing. It's just a cylinder. It's meant to represent the same body here. This is going to be the inertia. It goes in the positive sense of my degree of freedom. So it is going to be J1 times theta 1 double dot. So the mass moment of inertia times the angular acceleration is my inertia. Now I'm ready to move on to the lower rotor and draw its free body diagram. Right, so on the left side, I'm going to have that bottom gear. And then I have a shaft going over to that main rotor. That's going to go back. And then the back shaft there. Okay, so I need to illustrate on here the moments and the forces that act on the bottom rotor and the bottom shafts. So first, so I don't forget about it, I must have an equal and opposite force. Then this would be the force that the top gear's tooth exerts on the bottom gear's top tooth. So if it's F on the top going backwards, it's going to be F going forwards here. And this force is going to be acting, again, the radius now R2, from the longitudinal axis of the bottom rotor and the bottom shaft. And I'll establish a coordinate system. I will call this the y-axis, even though it is going to be parallel to the x-axis. And we are given that the positive sense of the angular position is theta. Looking at the right end, I have this rotational damper that is going to be exerting a moment. And once again, it will be in the opposite direction of the positive velocity, since attached to the wall on the right and then the shaft on the left. So its direction is going to be along the negative y-axis, and it's going to be the coefficient of damping, Ct, times the angular velocity, theta dot. And then the inertia picture, we're going to have the inertia following the positive sense of rotation, theta, and that will be J theta double dot. Now we've established our full free body diagram collection for this problem. We have these two bodies with inertia, the top rotor, the bottom rotor. Each one has its own free body diagram, and we have the forces, the moments that are acting on the bodies. So if the free body diagram is established, we can write out their equations of motion. And this is free body diagrams. All right, so looking at the top, I will call this my equation 1. I want to sum the moments around the x-axis from the left picture and the right picture. So based on my coordinate system and the direction of the positive rotation around that x-axis, which I'm also calling theta 1, let's see what we have going on here. I'll move left to right. Around the negative x-axis, or opposing my theta 1, I will have a negative ct theta 1 dot. Moving to the right, I have my torque, which when t is positive, it's around the positive axis, so a plus t. And then I'm going to have my force, which is going to create a moment around that x-axis. The way I've drawn it, and I've chosen to draw this kind of backwards into the picture, but as long as I'm consistent with its sign, if I drew that forward or backward, it would not matter too much. But according to this picture, that is going to be causing a moment around the negative x-axis. So this is going to be a negative force times its moment arm, R1. So 2 moments and 1 force that creates a moment around the x-axis on the left picture equals, and then I have my inertia, my J1 theta 1 double dot. Now I can go on to my second free body diagram and use it to write my second equation of motion. In here, I will sum the moments around this y-axis that I have as my coordinate system, where theta is the positive rotation around the positive y-axis. Moving left to right, in this picture, I have that equal and opposite F force, so that is going to cause a moment around the y-axis, the longitudinal axis. And in this case, that is going to be negative F, the force, times its moment arm, R2. And moving to the right then, I will also have a minus CT theta dot. And those are the only two forces, well, a force from F and then a moment from the CT theta dot acting on the left picture. And on the right, I have my inertia. I have, in the positive sense of theta, J theta double dot. I can only get 2 equations of motion because I only have 2 degrees of freedom, the rotation around the x-axis, the rotation around the y-axis. So I'm going to take these and I'm going to take them into the frequency domain. So 1a is going to come from taking equation 1 and doing a Laplace transform. So I will have a negative CTS theta 1. Going back, we are told the system is originally at equilibrium, so all of our initial conditions will be 0. So that's where I just get CTS theta 1 plus, now I already have capital T, it's a function of time. When I take its Laplace transform, I'm going to make it this, I'll call it fancy T. Since it's already capitalized, I have to do something to it to notate that I'm now in the frequency domain. So big T was a function of time, fancy T is a function of S. Minus F, that is the force between the top gear tooth and the bottom gear tooth. That also is a function of time, even though it doesn't explicitly appear that way, but that forcing can change in time because it also can depend on what the torque is, the torque input. So little f will go to big F times R1. R1 is a constant. There is going to be an issue with it that we'll address. And on the right-hand side, J1 S squared theta 1. Oh, and I do have to notate here these thetas have to be in the frequency domain, so they have to be capital theta. Right, so I have the Laplace transform of 1 to give me 1a. Now I can get 2a, again by doing a Laplace transform from 2 to get to 2a. I have negative FR2. Once again, that small f goes to capital F because I'm in the frequency domain times R2 minus CTS capital theta. So the theta dot goes to S times theta, and the lowercase theta goes to uppercase theta because it's now in the frequency domain. Times, or equals on the right-hand side, JS squared theta, and again, capital theta there. All right, so let's see what we have so far going for us on our outputs and our inputs. Our input, again, in the system is this torque, which is in the frequency domain fancy t. And outputs, I have so far theta, I have theta 1, and I've added 1, I have F. Right, so that force between the teeth. And at the moment, I only have 1A and 2A, 2 equations, 3 outputs. And again, I'm going to have another issue in a moment as well. So I need at least one more equation since I've identified 3 outputs. Well, I haven't used all of my information yet. There's another constraint in the system, and that was how the gears are meshed together. I haven't used my gear ratio equation yet. So I can use here n1 over n2, which are given parameters in my system, equal negative omega over omega 1. So I can establish that as 3, and then I will, right now I haven't done the Laplace transform yet, but again, n1 over n2, which are given parameters in our system. For external meshing, n1 over n2 is negative omega over omega 1. And what is omega? That's the angular velocity. That is going to be theta dot over theta dot 1. I'm going to rewrite this a little bit in 3a, because if we look at the right-hand side, I have a theta dot over theta 1 dot. I'm going to need to get to the frequency domain with this. I would rather not have a quotient because Laplace transforms don't work well with products or quotients. So I'm going to multiply through, so I'll say n1 theta dot 1 equals negative n2 theta dot. All right, so I'll write it that way instead, and now I will do the Laplace transform to get into the frequency domain. So n1 is a constant, so it stays out. I'll have an s, and then theta 1 dot goes to s times theta 1 equals negative n2 s theta. And actually here what I have is an s on this side and the other side. I can actually get rid of that, and I can go even simpler for 3c and just say that n1 theta 1 equals negative n2 times theta. All right, so what have I done here? This was one relationship I had for that gear ratio that is going to be that constant scalar between the angular position of the first rotor and the angular position of the second rotor, which is also going to be the ratio for their velocities, their accelerations, etc. But now I've included that information among my equations. So I now have a third equation, 3c, that I'm going to be able to use as well. So now we see at the moment we do have as many equations as we have outputs for theta, theta 1, and f. But actually we do have a bit of a problem because we have this R1 and R2. Now we needed those because when we took the moment, we had to do the force times the moment arm to figure out the moment from the force at the teeth. But if we look back, we're not given R1 and R2. We are only given N1 and N2. So we need to express this only in given parameters. So there's actually another output, so I'll cheat a little bit and call R1 an output, even though it is a constant, so it's not a function of s that we don't know, but I'm putting it as an output because we do want to make sure we eliminate it from being in any of our equations. And we'll see how we do that then in Mathematica, or if we were doing it by hand. But that means I do need one more equation now. But all it is the relationship for proper meshing or fully meshed gears, that the ratio of N1 to N2 equals the ratio of R1 to R2. And that will actually be a fourth equation that will be able to eliminate R1 and R2 and replace it with N1 and N2, which once again were given to us. So we have four equations, 4, 3c, 2a, and 1a, that we're going to use for the 3 real outputs plus 1 fake output, as we'll see when it eliminates it, and we have that 1 input of fancy t. So this one we definitely want to use Mathematica for so that we can simplify the algebra and it can do the heavy lifting for us. So I can start transcribing these into Mathematica. My first equation of motion, 1a, I have here a negative CTS theta 1. So to do, this is capital theta, I can do escape and then capital TH escape to do a capital theta if I want it to look consistent, plus, and here because it's fancy t, I can do escape capital T escape to get this fancier t, minus just a capital F R1 and double equals J1S squared capital theta 1. Okay, so that is my first equation of motion coming from that first free body diagram. And now I have it entered into Mathematica. Now I want to go to 2a, and that will be my second equation of motion. So I have here a negative FR2 minus CTS times capital theta equals JS squared times capital theta. And that needs to be a capital J. All right, so that is my second equation of motion, now entered also into Mathematica. I need to go to my equation 3c, bring that up, which is necessary. So that is going to be, this is coming from gear ratio. I guess I'll call it R1 for the first equation I'm using from my gear ratio in 3c. So N1 capital theta 1 equals negative N2 capital theta. And then what I will call R2 is coming from my equation 4. This will allow me to eliminate R1 and R2. So this is telling me, I'll put it in fraction form, my N1 over N2 is going to be equal to my R1 over R2. Those are my 4 equations for my 4 outputs. Oh, and you might think from the equations, isn't R1 and R2 not given to us? That is true, but we're going to see that the way it works out in this one, that because we're given these ratios, R1 and R2, that if we eliminate one, it's actually going to automatically eliminate the other. So when I do the solve, I can solve it for R1 or R2, and we'll see that we get the same results. All right, so those are the 4 equations we need. Now we can go and solve. So I need EOM1, EOM2, R1, and R2 are my 4 equations. And then my 4 outputs, 3 of them are actually functions of S, and the transfer function I get will be meaningful. And then I'll also get something for R1 where it doesn't really mean anything, but I do need to solve for it so that I can eliminate it from my equations. So theta, theta 1, capital F, and R1. So remember, when I do this solve, the variables I list here will not appear in the right-hand side of any of my equations. So for theta, theta 1F, that's great because I want their transfer functions. We'll see what happens to R1. So going through this solve step, let me get rid of the double list here. I get theta, theta 1, F, and R1. So R1 is really not a transfer function. We see no S's there. It's really just re-giving us R2, just written in a different way. But if you notice, what do we have going on here? Well, on the right-hand side, we have N1s and N2s, but for none of them do we have an R1 or an R2. If I replace this with R2 in this example, I get, well, it solved it for R2 instead of R1, but still the right-hand sides have no R1s or R2s in them. So I'll just go back to R1. So 3 transfer functions that are usable, and then I have R1. Going back to, well, what were we trying to find here? We want omega over t. Omega is the angular velocity of the second rotor, but because I'm in the Laplace frequency domain, that omega doesn't appear anywhere because everything is in terms of theta, theta 1, and f. So what we want to do here is actually start with theta, because we're going to realize there is a relationship between theta and omega. So let me actually first get the transfer function for theta. So I will call this TF theta, and that will equal, so I want to take this whole right side here, and I want the transfer function, so that is theta over t. So I will delete t from here, and this is my TF theta. That is my transfer function that takes me from t on the bottom to theta on the top. Now, it's not in a great form yet, so I want it to be rewritten here, so I can use that standard collect, the numerator of TF theta and s, and then the same thing for the denominator. So now I have this nice expression here that is my transfer function from t to theta. I'll go back to handwriting it and we'll see how this actually helps us get to where we ultimately need to go in this problem. I can transcribe this. Remember, this is not g yet. This is theta over fancy t. And that will be a negative n1, n2 in the numerator. And then the denominator, I have this jn1 squared plus j1n2 squared, s squared, plus a ctn1 squared plus a ctn2 squared times an s. I'm not quite where I need to go yet. I want omega, capital Omega over t. That's the g I'm looking for. Well, fortunately, in the Laplace frequency domain, it's actually easy to go from some variable to its derivative or to its integral, because omega is going to be the time derivative of theta. And to do a time derivative in the Laplace frequency domain, all we have to do is multiply through by an s. So it is true that capital Omega equals s times capital theta. Multiplying by s takes a derivative. And we already know that because we had to do that to go from 1 to 1a and to go from 2 to 2a. We had theta dot, it became s times theta. Well, theta dot is just omega. It's another way to express our angular velocity. So what can we do here? I have this transfer function, but I want to get to g equals omega over fancy t. Well, it's actually pretty easy because I know omega is s times theta. I can take this transfer function I just came up with, and I can multiply the right-hand side by s and the left-hand side by s. Well, what does this let me do? Now I have an s times theta. That is just capital Omega. And I did the same thing to the left side as the right side, so let's see what happens. This is equal to negative. Now notice I'm multiplying by s. My denominator has, in the previous transfer function, an s squared and an s, so I can actually just start canceling some things out. n1 over n2, and down here I will have a jn1 squared plus j1 n2 squared. Now the s on top and the s squared on the bottom are going to reduce, and I'm left with just s, plus, I'll pull out the ct here, n1 squared plus n2 squared. The s on top, the s in the denominator cancel each other out. And I'm left with then no s in the denominator. This is the transfer function that I was looking for at this point. Now, along the way, and using Mathematica, I already solved the transfer function for theta over t, which led me to omega over t. ultimately what I needed. I could have found the relationship between omega and t, which I have in the Mathematica, and F and T, which if I wanted to know how the force varied with the torque, I could find that as well. And I was able to eliminate R1 and R2 and use only the given parameters, the number of teeth on each of the gears. And notice in this one on the right-hand side that I actually have a negative out in front, which typically we haven't been seeing based on degrees of freedom that we chose. But what this is showing us is when the torque is positive, because of that external meshing of the gears, when I apply a positive torque, it's more or less going to cause the velocity of the second rotor, the bottom rotor, to be negative or the opposite direction. So if I put a clockwise rotation or torque on top, I get a counterclockwise on the bottom. If I put a counterclockwise torque on the top, I will get a clockwise velocity on the bottom. So that is the transfer function that we were looking for in this problem. So a recap of how did we get here? We started with these two rotors that we were told were meshed together with gears, fully meshed together with gears. They each had a mass moment of inertia. So for each rotor, the top and the bottom, I drew a free body diagram for each. I had the forces and moments that acted on the top rotor, and then its inertia. We were told theta 1 as its degree of freedom, which I just stuck with its direction, and then also established an axis that theta 1 was positive about. So I arbitrarily called it x so that I could sum moments around an axis in the equation of motion step that was next. Then the second free body diagram was the bottom rotor, and I have the force and moment that act on it, and then its inertia. So its mass moment of inertia times its angular acceleration. From free body diagrams 1 and 2, I got equation of motion 1 and 2 by summing the moments around the x and the y axes respectively for each of my free body diagrams. But when I looked at 1a and 2a after taking the Laplace transform, well, two things happened. When I counted up my outputs, I have theta, theta 1, and f. So three functions of, well, frequency. And then my input, fancy t, which was the Laplace transform of capital T, my input torque. And another problem is I have R1 and R2, and I was told in the problem to put only things in given parameters. I'm not told what the R1 and R2 are, I'm only told what the number of teeth are on each of the gears. So I actually need two more equations to eliminate some of these variables on the right-hand side going forward. So I came up with equation 3 using the external meshing relationship that the ratio of the number of teeth is the inverse of the angular velocities. It's also the inverse of the angular positions and the angular accelerations, it turns out, and that's what I used here. So n1 over n2 was negative omega over omega 1, negative because of the external meshing. And omega is the same thing as theta dot. Omega 1 was the same thing as theta 1 dot. I rearranged it a little bit so when I do a Laplace transform, I don't have a quotient. And then that simplified down to 3c, a relationship between theta 1 and theta. They have a constant scalar multiple between them. And then my fourth equation related the number of teeth to my radii of the two gears for fully meshed gears. That gave me the four equations for my four outputs, three functions of s, and then one extra one because I want to eliminate R1 and R2. Going through Mathematica, I let it do the algebra, and I came up with the transfer function that took me from the input torque to my angular displacement, or angular position of the second rotor, capital theta. Now, this wasn't where I needed to go yet, because I wanted the angular velocity as my output, not its angular position. But I can start here, and it's going to be pretty easy to go to the next step, because in the Laplace frequency domain, multiplying by an s is equivalent to taking a derivative in the time domain. So, taking this transfer function, multiplying the left side and the right side by s, I can rewrite s times big theta as capital omega, and that's where I needed to go. So ultimately, I was able to find omega over t then after multiplying by s. and we got the final transfer function for this problem.